Okay, so the idea now is to try to, I realize that the first class I've kind of bombarded you with quite a lot of material if you had never seen that before. So now I'm going to kind of go back to it and try to illustrate it with examples. So we're going to discuss two things, and I'm going to introduce them now. One is, in fact, the first half, then I'll try. One is this Schlegel model, which is just, it's a little chemical reaction that's written there. It has a feature that it will lead to metastability. That's why I want to use it. And so, it's a molecule of A plus 2 of S give 3S, and 1 S can give a B, and these are reversible reaction. Okay? And let's imagine that we look at this system really to make things simple. Let's imagine that there's only species S that can vary, and that the concentration of A and B are kept fixed as if it was a reservoir. If that's the case, you can convince yourself, like if you know a little, I suppose that this is really something that most of you must be familiar with, which is that if N is the number of molecules of species S and V is the volume, and you work in a well-mixed system, you can have that, you can gain a molecule of S with this rate, and it's scaled in such a way that all the rates are on the right scale, in the sense that it needs to be proportional to the volume. So here's the volume times the concentration. So this is NB, and here is the well-mixed systems. It's a ternary reaction. These three molecules need to find one another, and so it's one pick the other, etc. So you get this product, and you divide by V squared. That this has a proportional to V. Similarly here. Okay, and the right limit to look at this system. So you prefer that I make it a little bit smaller and we see more things, or it's good like that? Good like this? Okay. So, if you say that V is large and N is large, but that you keep the concentration, that's CS, of order 1, right? Well, you can, so the rays that are written there give you what's written here. So let me try to put them both together by making it tiny little bit smaller, like this, right? Which is that epsilon is now 1 over V, and so what you have is that there is a rate of creation and a rate of annihilation of one molecule. So that corresponds to plus or minus epsilon here, because it's 1 over. We have rescaled things like this, right? And the lambda plus and lambda minus are these guys. So they themselves depend on epsilon. Okay. All right. So we're going to get to that example in a minute. Here's another one, which we're going to combine the two, just to fix ID. You have L boxes, population Ni every box. The sum is preserved, and let's imagine the no exclusion principle. Like the simple thing you can think of, just diffusion, is that the probability to hop out of one box is proportional to the number of molecules of that box, and that leads to a change where you lose a molecule there and you get it in the adjacent box. We do in 1D. Okay. And here the right scaling is you take N to infinity and I to infinity, but you keep this fixed, and you get this generator, where the EI is just the vector where every entry is 0 except 1. There was a confusion about that, like someone asked me a question, so let me... these are vectors, right? The I here is not a component of a vector. It's just the vectors that are indexed. There's is the unit vector, if you wish, in that space. Okay, you get this. All right. So these are the two examples we're going to play with. But let's start. So this was, these, by the way, are the notes that I was advertising. So let's look at the Schlegel model, and what I'm going to discuss is the thing of Rubin-Zaki. So here's again is the Hamiltonian, and these are the rates when you take the limit. Okay, and the reason why this model is interesting is that if you look at the law of large number, so this is really chemical kinetics at this level, right? This is what you would get, law of mass action. What you get is that this guy is simply lambda plus minus lambda minus, as obvious from here, right? And so if you think about, and this is why the model is interesting again, if you look at this x dot is equal to b, this is motion in one dimension. And so you can plot what B of x is as a function of x. And if you adjust this parameter the right way, lambda, you can get that this B as a graph which is like this. This is the B. And so it's a one-dimensional thing. And so the fixed point are where B is equal to 0. And if B is negative, the system moves left. If B is positive, it moves right. So this is a stable fixed point, unstable, and stable. So this problem is interesting because it says that at the level of the chemical kinetics, the law of mass action, you have bistability, right? If you were to start the concentration anywhere in this range, it would end up here. Anywhere in this range would end up there. But eventually, the fact that you are working with a volume that is finite would lead that you could get oscillation of this chemical. Okay, we want to understand that. Okay, so this system is easy because, okay, so now it's a different picture. You can look at the Hamiltonian because it's a 1 degree of freedom. So the Hamiltonian is a function of 2 dimensions. And so what I'm showing you here is the level set of this Hamiltonian. In this case, because there's only 2 reactions, you could also look at the Lagrangian, you can solve it, everything can be done. But I'm looking at this. So the level set of this Hamiltonian look like this. Okay? So don't confuse these 2 pictures. This is really theta, the conjugate momentum, and x. The white line and the dashed white line are the level set h equals 0. Here the Hamiltonian is negative, 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 negative. Here it's positive, positive, and positive. Okay? You see that theta equals 0 here. It corresponds to the law of mass action, which is the law of large number also, which means just motion this way and that way, or this way and that way towards this fixed point. If theta is equal to 0, this is the only thing that can happen. But you can see that if you look at the solution of the full Hamiltonian system, the one where you include the fluctuation, there are ways, there are trajectories in this system that go from this guy to this one. In particular, you could, you could think here, take, for example, that one would do that in finite time. Okay? And correspondingly, there's this trajectory, for example, that would do the reverse reaction. Right? If you do the info over t, if you look about all this trajectory and you look at the one that has the minimum action, if you also minimize over all possible time for this, what you end up having is that the one that go from there to there is just this, the one that follow this level set. And the back reaction is this. Okay? And so, you can calculate the action along this. This is this quasi-potential. So you can look at the quasi-potential starting from there to go there, or starting from there to go there. I'm not going to discuss this graph too much because I can do something. It's all to discuss, to get the. Maybe this. Let me show you this more. So in other words, okay, let's forget about this graph. It's explained in the note, but so this is actually telling you that. So okay, maybe there's something we need to. Let me discuss this. I need to discuss this. Okay. That's right. Yes. So let me explain this. So this is okay. So this guy, the yellow curve, is the quasi-potential to go from x minus towards any x. Okay. So let's look what it does. This is. I had a question about caustics. This is caustics at. Okay. So here is this quasi-potential. If you start here to go this way, it increases like that, because you need action to go that way. Here, if you vary x, so I'm looking at the quasi-potential from x1 to an x minus, to an x. As you vary this, you need the quasi-potential increases until you reach this unstable fixed point. Once the system reaches the unstable fixed point, to continue in that direction, no noise is needed, no fluctuation. So the quasi-potential stays flat at that value. There is no to go at any point between here and here, the cost is the same as just reaching the unstable critical point. But once it gets there, it starts creeping up again. So this is one quasi-potential. The other quasi-potential is this one. Now, all of the theory that I'm describing here is something that is in the book by Wenzel and Fredlin. And they explain over there how you can do something which is called decomposition to cycle. And from these two potential, you can get a global potential, which is by patching them together. And that's the curve that I'm showing here. This is what I don't want to discuss. Because at the end of because it's a bit technical. But at the end of the day, the rates by which sorry, that's my each time it's going to go to sleep. So I cannot, it's actually good. I cannot talk too long before moving. Keep me in check. Okay, so the rate to go from there to there is the Arrhenius law with this barrier. The rate to go from there to there is the Arrhenius law with this barrier. This tells you that this is the stable phase, because the rate to go out is the barrier is much higher. Notice that there is no barrier here. Let me make that point very clearly. Maybe by repeating something, which is, okay, so this is which is that since we are in 1D, this B of x here, you can write that down as the grain of a potential. But that potential is not the quasi-potential. So it gives you the wrong answer. And in particular, this is very explicit here. What is shown here is that, so there's a couple of graphs. This is just Monte Carlo, where you compute the invariant measure of this system by increasing its size. Okay? And you see that, okay, you need to go to large size, but you see that what you end up having, remember that we are talking about chemical kinetics, so this should be Avogadro number, so it's not that big, but okay. So it converges towards this curve here. That's the one that you deduce from there. What I'm plotting here is minus the log of the PDF. Actually, it's not minus the log, it's just the log, because if it was minus, that's a misprint. In fact, it's just the log of the potential. If you were to flip that, you would get the guy back. So it shows that, this is showing that this large deviation result gives you the right limit. This dashed curve here is the potential that you would deduce if you say the B of x that we had from the law of mass action, I want to write it as the grain of a potential, which in 1D you can. In general, in higher D you cannot. But you see that this gives the wrong answer. In particular, you see that here you would deduce that the stable phase is there, whereas the actual stable phase is here. So it's really completely wrong, right? It's not, okay. So that's what's happening with this. Is this clear? Yes? Okay. So now, we're going to do this. Let's imagine that you have a system, it's a Schlegel model, in which you have boxes. In each of so it's a bit of this is a model that's been played by Lubensky and Tanase Nicola. There's a few. So you have boxes. In each boxes you have a well-mixed reaction, and then you can have hop of the molecule within the box. So molecules only react in their box, but you can diffuse by hopping from box to box. So if you write down the Hamiltonian of that, there is two Hamiltonian. There is the reaction Hamiltonian, which is the same as before, but superposed on every box. And then this is the one that you get from the diffusion, the discrete diffusion. This is hopping from box to box. Okay? The continuous limit would be this, but let's not discuss that. Well, okay, maybe we can, maybe one thing. So, maybe to make the connection with this is a diffusion, which is that if you were to expand this, if you take, this is a limit epsilon going to 0, like with the size of the system. If now you were also to take the number of boxes to go to infinity, you could, this variable could become continuous, and then, this guy would reduce to, the sum would become integrals, and in that case, that one you still cannot expand, but this one would become quadratic. Okay? This, in fact, is the Hamiltonian that you would get formally from the Dean's equation, for those of you who have seen that. Now, the reason why I write that is because, and that's going to be important in a minute, is that, if you look at the law of large number associated with this, is this reaction diffusion equation. The one we're actually going to look at is a spatial discretized version of this, if you wish. But if you look at this looks like, it looks like an Allen Kahn or Ginsburg-Landau type equation on the energy which is written below. So you could again be tempted to try to deduce the Arrhenius rates by looking at energy barriers in this energy. And I'll show you again that that's completely wrong. Okay? Bear with me for a minute. Okay, so let's look at this model. Let's go by steps. First thing, let's take 2 boxes. The reason why I want to take 2 boxes is because then I can show you, no, it's a 2 degree of freedom, so I can still show you the trajectory in their x space, in the position space, even though I cannot show the trajectory in position and momentum because that would be 4-dimensional. Okay? But these are the trajectory in this 2-dimensional space, 2 boxes. Okay? Okay, so the picture is symmetric this way because it's 2 boxes and they are periodic. These flow lines that you see are just the flow line of the law of mass action. Right? So the law of large number, the ODE that you would get if you take really the limit as epsilon volume going to infinity, and there is no, you don't take into account any fluctuation. And so you see that you get something which is actually fairly complicated because you get that there is a 2 stable fixed point here, and then there are 3 unstable fixed points. This one with 2 unstable direction, and this one with 1 unstable direction and 1 stable direction. It just so happened that's what happened for this specific system, for the parameter that we took. Okay, so think equilibrium here. So if you had to think equilibrium, the system should, you would try to identify heteroclinic orbit that allow you to go from one stable fixed point to another stable fixed point going by an unstable fixed point. Again, being this argument that at equilibrium, if I know where I go from the unstable fixed point to the stable one, I should time reverse. So this dashed line here is one such heteroclinic orbit. There's another one here, and then of course there's one that is below that. Then you can calculate what are the paths by which the actual reaction occur in this large deviation limit, and this is the path that go from there to there. Sorry. This is the path that go from there to there. And this guy is the preferred path that go from there to there. And you see that the paths are different, and they are different from this heteroclinic orbit. This is a signature of the fact that what's happening here is a non-equilibrium transition. Okay? And, okay, so is that, yes? Then you can calculate what is the action along this path. So this is just, the integral of this. So this is, you just calculate what's the action as it accumulates along the path, measured by arc length, because you can do it. And this is the action as it accumulates from the blue one and the one over the red one, the orange one. So the total action that you have here, right, is a number that is E, the rate is E to the -1 over the volume times that area. Okay, so if you see this, you can immediately deduce that this guy, the blue one, right, is the stable, because the rate to escape it is much higher, much lower than the rate to escape the other one. So the time scale are completely different here. So there's a phase transition, right? This system this is not a phase transition. There's a preferred phase. Okay? Now what we're going to do in the next little calculation is that, so here, that means that by doing this calculation, you can deduce which one of the 2 phases, which are stable fixed point of the law of large number or the law of mass action, is actually the preferred one. Something that you cannot do if you just have the law of mass action or the CLT above it. Okay? But what is now a phase transition in this system is that you could imagine that you tune a parameter, one of the rate constant, the concentration of A or the concentration of B. And then as you do that, you could perfectly imagine this phase portrait can change, like the fixed point could change location. We will see that in the example that they don't, but that's irrelevant. But more importantly, this curve could change. You could have that this guy goes up, for example, and this guy goes down. So what would be a phase transition? It would be the value of this control parameter where the area flips. Right? If if at some value, say, of the concentration of A, this area becomes bigger than that one, that means that the preferred state from one becomes the other. That's the phase transition, right? Because it means that with probability 1, essentially, you will find the system now, instead of being, this guy, it would be on the other one, if you wait long enough for this. It's a first-order phase transition, okay? Like water freezing, but this in a non-equilibrium system. Okay, now, this is what happens if you take 40 boxes. I'll show you how these calculations are done later. There's a bit of numerics here. This is done numerically, obviously. So if you have 40 boxes, so what you see here now, you need to, these are level sets of the transition pathway. So if you take a slice here, and you were to look at the value of the function along that slice by reading this bar, you would find what is like the state of the system. So, for example, here, where it's all blue, that means that the full system is at 0.5, and when it's all yellow, it's at 1.6. These are the homogeneous phase, where the value of all the boxes are the same. They are on the diagonal of the two-dimensional example that I showed before. And they are the stable fixed point of the law of large number. Just going to do this so that it doesn't go. Okay? Now, when you look at this, so there's three graphs. So this is what happened along the, to go from there to there, to go from there to there, by the path of minimum action, so the one that solved this Hamiltonian equation. And this is along the heteroclinic orbit. Okay? So, for example, if you go from here to here, if you look at this, right, and this is the path which crosses the separatrix. So let's just look at this. It means that when it crosses separatrix, it's happening by a nucleation of the other phase somewhere in the previous one. Is that clear? Yes, because if you were to look at this profile, right, it was there like this, and now it has become with a bulge like that, and then this bulge will grow and occupy the full space. And this is the action, and this is the corresponding theta field, if you wish, the optimal noise that is fluctuation that is needed for that. That's the interpretation it has. And these are the action. This is the path that goes backward. And these are the paths that go forward and backward if you were to use the heteroclinic orbit as test function. So you can always use the test, you can say, okay, I can take the heteroclinic orbit as test function, see what is the action. The action along this path is always bigger than the one that you have calculated along the minimizer. Okay, so this is the way you have, nucleation for the transition from one state to the other, one phase to the other, one metastable state to the other, due to finite fluctuation in these systems. Okay? Yes? Okay. Now, you can redo this by varying control parameters, okay, to look at phase transition, like I explained before. So now what I'm going to do here is that the only parameter that we're going to play with is the diffusivity, is the rate at which the particle can go from boxes to boxes. Yes? There is a reason for that. Let's go back a little bit and think. I told you that this guy gave the wrong answer. Right? Okay, so here is, if it were to give the right answer, here is something that you would deduce immediately. This is the energy in the continuous limit of this system. Right? For homogeneous phases, the energy only depends on the difference of these two factors, which is minus the derivative of that give you the rate. But it cannot depend, this doesn't make any, this is not important, because this is just, for the homogeneous phase, this guy, right, is, the derivative is 0. So this doesn't, right? So that means that on this energy, the height of the barrier can vary because of this, but the value of the energies that you have is independent of alpha. That means that if you vary alpha, they can be changed in the system, but the phase that is preferred should be completely controlled by what was controlled here, And you cannot have a phase transition by varying the diffusivity. Is that clear? If you are thinking equilibrium, okay? So to verify that what we get is a non-equilibrium result, we're going to see whether we can induce a phase transition just by varying this. So that's what is done on this little graph, is that, so this is, this is sort of a lot of calculation, numerical calculation, but if you have the right tool to do it, you can actually do it fast. You redo this calculation by varying the diffusivity. Each time you calculate the quasi-potential to go from here to here or here to here by doing this calculation. And then you plot the value of the quasi-potential. And these are the value of this quasi-potential. Here I apologize this because these are notation in the paper. Here rho denotes what is the field, is the variable and not the density. So this is the quasi-potential. The two graph here is the quasi-potential to go from rho minus to rho plus or rho plus to rho minus. Okay, so it's just two numbers. And they are plotted as a function of alpha, this diffusivity. And what you see, well, is this, which is that the state that has the highest quasi-potential to go to the other one is the one that is not preferred. Okay? Since you just count in two rates. And so when they cross, this is the equivalent of the crossing of the, the height of the two energy barriers. That's a phase transition in equilibrium. So there is a phase transition that occurs here. But again, this is a phase transition that has been induced by the diffusivity, the diffusivity coefficient. So that tells you that the path matter, that is really non-equilibrium, because by the argument that I just explained before, otherwise it would not be possible in a standard Ginzburg-Landau system to induce a phase transition just by changing the diffusivity. And here you can. Okay? Is there a question about this or? I don't know, to be honest. You see there's a kink here. So there are things that are interesting. That you see this little kink there? And that's about the fact that in this system, I kept that a little bit on the rug, but there were questions. You can have caustics or, in general, when you do this, when you calculate this quasi-potential, you're solving an Hamilton-Jacobi equation that you have obtained by taking the viscosity limit of a viscous Hamilton-Jacobi equation. So you can have that there are multiple solutions. Is multi-branch, and then you need to be able to pick which is the right branch. And when the branch cross, that's a caustic, and then you can have non-differentiability. That's exactly what's happening here. So there is like one branch that continue like that, another one that is like this. For this guy, which is just going one way. This one is smoother. I don't know. I don't know if one of them. I think one of them is close. From the graph above here, you see that this one is homogeneous. The heterogeneous orbit is not. This is homogeneous. It's right. It's like a whole block. There is no variability in space here. Here there's a lot of variability in space, and here there's a little less. Whether one of these guys at some point become, I don't know. But okay, there's a question for Ruben, or I can go back. I can get back to you about this. Okay, so this is just, and then I move to another example. This is checking these results. So let's check this result by doing a little bit of Monte Carlo. So here, this is not very surprising, is that if you initiate the boxes with a concentration that corresponds to this step, and then you do Monte Carlo, you can do Monte Carlo in this system using the BKL, Bose-Carlos-Leibowitz, which is also called Gillespie algorithm. This is kinetic Monte Carlo rejection-free. I can explain that to you later if you want. You can actually look on how the evolution of this unstable initial condition evolved by the law of mass action over the boxes. That's one of the set of graphs. And then the other one is just the solution of the law of mass action. And you see that it tracks very nicely in time what's going on. Of course, this is all going from unstable to stable. So you don't need the noise here. This is law of large number. This is a bit more subtle, which is that, okay, so by definition, as I said before, if you want to do Monte Carlo and try to get phase transition information, it's very difficult because you need to take the volume going to infinity. But when the volume goes to infinity and you use your Gillespie algorithm, something happens all the time because the number of particles that can react go to infinity. So it's a bad scaling to do. So not only your time step goes down because something is always reacting, but so on this faster and faster time scale you need to compute, there is something slower and slower that happens, which is the going above, this exponentially long event. Right? But what you can do is you can prepare the system in such a way that the unstable phase is near spinodal. So then you are at the limit of where large deviation should work because the barrier the quasi-exponential is small, but there you can do the Monte Carlo. And so what this is done here is just calculating the mean first passage time from one phase to the other, from this very unstable metastable phase, if you wish, unstable under noise, by varying the size of the system. And this is the prediction from large deviation in log scale. And this is what you get from Monte Carlo. So you see it does the right job. Okay? Now, there is something that I have not discussed here, but it's very important, is that if you want to talk to chemists, they'd like to know the rate with a number, not like a log. So they like to know what, not only the slope, but they like to know what is or what is the height of this curve. That's a prefactor calculation. That you can also do because you can go to next order, but that's the topic of another set of lectures. I don't want to do here. It's like in the context of the WKB, it's like instead of doing WKB, you would go to physical optics. And that can be done. It's a Gaussian integral that you need to calculate. Okay? I'm not going to discuss that here. Now, I want to discuss a little bit. So, I don't know if people here are interested in numerical calculation. But I do believe that, for these models, without numerical calculation, you won't be able to do much. And this is really like, in a way, the motto of applied math, which is calculations that are impossible to do maybe by, brute force simulation. You find a way to do them by doing some asymptotics, and then when you hit something that you cannot do analytically anymore, then you do numerics on this simplified. So that's solving this instanton equation. So I'm going to describe how to do this for a little bit. Okay? And I don't know if people are actually interested in numerics, but I know people are interested in machine learning, at least a few. I mean, every person below 30 should be interested in machine learning. So I'm going to describe, so let's go back to this problem for simplicity. Okay? Suppose you want to minimize this, right? Okay, so I'm going to describe intense frustration of research. For 20 years of my life or so, I have, with collaborators, we have developed numerical methods to do this minimization by standard numerical method. And we have called them MAM, GMAM. They are like moving curves. It's very painful to do because, in general, this Lagrangian here has not only a temporal aspect, but a spatial aspect. We are talking about PDEs. When you talk about PDEs, there's all of these CFL conditions, which are stability conditions, which is that when you write down scheme for that, you need to be super careful about how you write the scheme because otherwise it's unstable. Okay? And on top of that, it's not always possible to do things that are unconditionally stable. They're only conditionally stable, it means that you need to take small time steps. And on top of, because the problem can be stiff. For example, if this Lagrangian here, I'm going to show you one that involve a Laplacian, then when you take the Lagrange equation associated with that, you get a double Laplacian. If it's a conservative model, there is the two Laplacian already here, you get 4 of them. That's 8 spatial derivative. That's like nasty if you want to do PDE. Okay? So we developed many of these approach, and I'm proud to say that we basically are the only one who have used them. Like, not much interest. We have made the code available, but okay. So now we're gonna decide. We know there is like, and this is the frustration, but at the same time, like it's like, no, there is machine learning. Okay, so I'm gonna describe more in the next class things that you hear if you're really willing to put the effort into it. Everything that I will describe you can do by classical numerical method. It's just much harder. Okay? Next class, I will show you problems where classical numerical method just can't do it because of the curse of dimensionality. Here there's no curse of dimensionality. But I'm going to show you how you can do this calculation, like the one that I showed before, in ways that, like, you know, it's almost like magic. It really feels like cheating, which is that instead of having a PhD student that does a thesis on this, you can give it as an exercise to do in a week. I mean, like, so the idea is very simple, and if you have played with neural network, you know, is that we're going to represent the solution as a neural network. We're going to view the objective as a loss for the network parameter, and we're going to optimize the parameter by stochastic gradient descent. Okay? So maybe not everyone who knows what a neural network. Maybe I should, but well, okay. If I ask who doesn't know what a neural network is, I might probably have less hands, but I don't want to have people being singled out. So who knows what a neural network is, has played with it? Okay, I'll assume that at least a few hands were not raised. So let me try to explain this. Imagine that this is this, you know, function of space and time, and let's imagine that this is, you know, we're going to look at that, in fact, in a minute. This is the minimization I want to do. In fact, we're going to look at that with additional gradients. Okay, so what do you do? Okay, so yeah, okay, so here, now there's going to be a theta, which is no longer the conjugate momentum. Is the set of parameters in the neural network. Okay, so erase from your memory, theta is the momentum, and these are the parameters of the neural network. So here's a neural network is really just a function representation. Okay, so here would be the simplest one. You organize your t and x, time and space, into a vector. You multiply that by a matrix that doesn't need to be a square matrix, and you add a bias. You pass it through a nonlinearity, say a ReLU, or something which is more differentiable than that. And then you repeat. And that's a fully connected neural network with depth L. Okay? The parameters here are these guys. Right? The ensemble. So this is not what we use in practice, but it's just to illustrate. In here, the architecture is fixed. So the depth of the network would be fixed. The shape of these matrices would be fixed, so their dimension. But all the entries would be parameters that you can adjust. Okay? So if you put enough layers and these matrices are sufficiently big, the expressivity of these neural network, even fully connected like that, is enormous. Especially in cases where you just want to represent the function that at the end of the day is scalar valued function of one time and x in 2 or 3D. Okay, so you get that. And then you do two things. I wanted to write that on the board, but I was hoping to have this, so I cannot do it. So I'll just flash it through here, which is that now, if you put this ansatz into the Lagrangian for this case, then this becomes a function of theta, the parameter in the neural network. Okay? So you're almost in business, except that this involves integral over space and time that you cannot do analytically. Right? But you can do them numerically. I'll go back to this in a second, what I just said. And so what you do, for example, is that you do an empirical approximation of your loss by representing the time integral, say, as a Monte Carlo over times that are drawn uniformly. You could put a grid if you want, but it's better to do this because we're going to do a different batch at every time, so you eliminate any impact of the grid. If these guys depend on time, on space, and you need to do a spatial integral, you also do it by Monte Carlo, by drawing your point uniformly on the domain or doing something which is more elaborate. Okay? So now once you have done this, you have an empirical loss. This allows you to evaluate this loss. Okay? And now you do gradient descent, which is that at every step, given you start with the value of your parameter, at every step you evaluate the empirical loss by the method that I explained above, and then you do a step of gradient descent, then you draw parameters, you draw input again, and you repeat. Okay? And you do that until convergence. Okay? This method is called physics-informed neural network. Why? It's because there is no, in the standard machine learning problem in data, you have input data, output data, labels. Cats and dog pictures, and then the label, which is a cat or a dog. Here, there is nothing at the beginning. There's just the loss. And in some sense, you generate your own input data, and the output data is not necessary because the loss itself gives you what, the value that you have a loss that you need to minimize. It's not like, okay. And then you repeat. Now, why is this so easy? First of all, because everything has been pre-programmed for you if you use TensorFlow, but there's a few features that really makes your life really easy when you do that, is that this function here, this function that you're using to represent your solution, is something that is analytical. It's a function. It's not like putting in on a grid, okay, like you would do with finite element or grid-based method. This is an analytical function of t, x, and theta, which means that you can calculate all of its derivative to arbitrary order analytically. There is no discretization error. What's more, the modern package of machine learning do that for you. You just need to specify the architecture, and then the value of the loss, and all derivatives that are being done for you analytically. So the only approximation that you are doing here are twofold. One is that when you look at your neural network, because the number of parameters is finite, this is an approximation. There is no guarantee with a finite number of parameters that you will be able to represent exactly the solution of your problem. In general, you cannot expect that to be true. But in practice, first of all, there are results that tell you, this universal approximation theorem, that tell you that if the number is large enough, you can get result to arbitrary precision. And in practice, we observe that these neural network, these or the other one that we use, are actually very, very expressive, meaning that the approximation power is enormous. They really do a good job. Okay. That probably would be asking for too much, because all of this is typically, it decreases like a square root of the number of parameters. So the conversion is more like these methods at the end of the day needs to be more understood in the realm of Monte Carlo, because there's a sampling aspect which is both for the xi and the xj, tj, but also the way these parameters are being optimized. Okay, when you do the calculation twice, you don't get twice the same answer. There's a kind of they are random with randomness from the initial condition. Okay, there are results like that. In practice, you take a neural network with 4 layers for this problem, and matrices that it works a charm. Okay. Okay. Well, I mean, I don't know if I need to make a few comments about the comparison with standard numerical analysis. Well, standard, I mean, it kind of is very interesting that it like almost all of the know-how goes out. Because when I was student, I was told nonlinear representation never use because it leads to non-convex optimization. You won't be able to do it. Turns out that's not true. If you make these neural networks sufficiently big, they find something which is a local minimum, but it's a very good one. It gives an excellent job. Okay. The other thing, which is why do they find good minimum? Is because we over-parameterized like crazy. We use, in fact, more parameter that we would need to represent the function on a grid. Imagine that our standard numerical analysis, I grid space and time. Okay? So to represent that function, I only need the number of parameters, which is to represent the value of the function at the grid point. When you do neural network, you could actually try to do that. So that would mean instead of doing this, the empirical loss by doing this, if you were to do this on a fixed grid, okay? Then you would say, well, I don't need that many parameters to represent this. In fact, I only need maybe one weight at the end here. That's all. But you don't do that. You over-parameterize like crazy. You have millions of parameters or billions in situation where you should only have 100. Okay? that works better for conversions in time of the stochastic gradient descent. But at the same time, it breaks another dogma that you were told, which is never over parameter, because otherwise you could overfit. Turns out they don't overfit. And okay, this is an active area of research and something I'm working on, but that for another time. And many others are working on, of course. In practice, it works. Okay. Let me give you one example of this. That's kind of, yeah. This is what we do here. You could potentially do a non-uniform sampling. One of the advantages of these methods also is the enormous flexibility, which is that in standard numerical analysis, if you say, you write your code and you realize it doesn't work, you say, okay, I'm gonna change the representation of the function. Typically, you're back at square one, and you need to redo all the CFL analysis. Here, you just change. So, if you look at your solution and you realize that stuff are going on at a given time, you can, even during the calculation, decide that instead of sampling the times uniformly, you're going to put more time there.
How does the network make a smooth functioning time? Because if you sample uniformly, you get due at different times, right?
Yes, but think about this in the following way. So there's an approximation. There's an approximation in this line, right? But where there is no approximation is that this Lagrangian here involves time derivatives and spatial derivative of this function. Okay? These are calculated analytically. In other words, in the standard method, you would grid the time, say, but also do a finite difference for this. Here, there's no finite difference. Okay? And so you know that from result from stochastic approximation, Robin Monroe, right, that if this is like online learning because you redraw the batch, right? And you can do that without ever, it's one gigantic infinite epoch because you can keep doing it. So you know that if you do that and you do the right scheduling of this guy, of the learning rate, so you shrink it, like Robin Monroe tell you to do it, you know that you will actually converge. There will be no overfitting for this type of model, and you will converge to something which is analytical again, right? Let me put that this way. If I want to represent the solution, which we will do, right? I plot them. We're going to plot them on a computer. When you plot them, you plot them on a grid. But that's something that you do a posteriori. When we do this calculation, we have an analytical expression for the u of theta tx, which is just this guy. If you go back, it's this. It's just at the end of the day, what the whole procedure does is that you have fixed this thing. All of these functions are analytical, and you just through the training decide the value of the entries of these matrices that you will need to use. And then once they have converged, you keep them at their value. Okay? So, but then you have access to this, so you can evaluate this at any point. Right?
So you say that if you overparameterize like crazy, it's better. So you try to see if you have a double descent curve in this example.
But you cannot check that here. You could. Okay, so okay. Yeah, you could. Sorry, let me rephrase. If you were to fix the t and the x, right, on a grid, then you could do this calculation. But we never did. We always redraw the batch because it's very easy. So by definition, we do online learning. Okay, so there is no double descent because, well, you never over. The only thing is, being careful about the learning rate. Okay, and as I say, all of this is done automatically. Even the optimization of the learning rate is done by Adam and all of these things that are in these packages, which is again like for someone like me is a bit of like using these black boxes kind of makes you sweat a little bit, but these are black boxes that have been used by so many people at this point, much cleverer than me, that you can trust. It works because if there's anything that's a bug or anything, there's a huge community that actually self-correct things. So they are very reliable. All right, let me show you one example of this. which is, I'd like to convey the pain of doing this by standard numerical method, but I think I'm going to fail. But okay, so suppose you look at this problem. This is a problem that sits with Eric Simonet and Ruben Zakin. And I'll finish with that. We're almost done. I just need to describe a little bit what this is. So we're going to look at what's called active model B. So it's a bit of a model that, so it's, this is within the realm of these studies by Mike Cates and Julien Tailleux and others, where sort of they reproduce the Ginzburg-Landau type analysis of phase transition for non-equilibrium. So Ginzburg-Landau, what they did is essentially you postulate a free energy based on symmetry. Here because it's non-equilibrium, you need to postulate the dynamics. Okay, and so what you recognize here is Cahn-Hilliard, where this is the mobility and this is the chemical potential, except there's a twist. The chemical potential that you would get from Cahn-Hilliard, say, would be this. Yes? Diffusion reaction. Okay, it's the conserved model. And then what you add in the chemical potential, so why do I say this is like Ginzburg-Landau, is because this part of the chemical potential is the functional gradient with respect to this Ginzburg-Landau energy. But you add this term. Okay? And this term is not gradient. And like it's the first term that you can add that somehow preserve the same symmetries. Like if you do, and I'm not an expert on this, so I trust my kids, and okay, you do that. Okay, now you look at this system, and no, this is formal. You imagine that you add a little bit of noise. So we know that this is dangerous because the noise should not be added like an additive. That's what I've explained with Schlegel. But let's pretend here that that's okay. So you just add an additive noise. This as a SPD doesn't make any sense. But it doesn't matter because we're going to derive a large deviation principle for it. Not derive, but kind of postulate. So if you do that, right, so, I mean, it's okay, so let me repeat this maybe just to make sure everybody was with me. This would be the standard, the law of large number, if you wish, that you have postulated. Without that term, it would be the standard Cahn-Hilliard conservative equation. With this term, is non, there's no energy, and this is adding a perturbation. Okay, right, and this perturbation would be in detail balance if this guy were not there. Right. Okay, and to do that, this needs to be a spatial-temporal white noise, and this is the place where mathematically that doesn't make much sense. But now you can, if you write down, so the sigma here, what I call sigma is m1/2. And everything was a sigma, 1 over sigma square, all of my action. So if you write down the action here, okay, and we can discuss that offline, you get this. I'm writing it formally, so you get this is the chemical, the chemical potential. That's the Laplacian, and this is the du, and then you have this guy. So you should really think about this as the square of a field, and the divergence of its field is this. That's the way the action is written. Okay, so this is the large deviation action that you need to solve. So I can guarantee Ruben spent a big chunk of his postdoc into actually solving this by standard numerical method. Okay, and it's not easy because this is a Laplacian of mu, but mu involves a Laplacian, so you have two Laplacians here. You're squaring this. There is this inverse operator that needs to be. You can imagine that this is actually pretty bad, right? If you do this neural network, you just rewrite that as a square of the field. You say what is that field is the one that satisfies the divergence of that field is this guy. You add that to the loss as a constraint or a restraint, and then you parameterize everything by neural network, and you do what I just explained. Okay? Again, the ease of use is quite amazing. All right, so if you do that, so let me show you what happened. This is result from the standard America. So in this case, we took this system in one spatial dimension, 2 and 3. In one spatial dimension, the standard code worked. In 2 and 3, we didn't even try. But in one dimension, we compare with the result of this spin, machine learning, and then we use the machine learning to do things in 2 and 3 dimension. Okay? Now, what you see here, and I'm going to try to explain that. I have a couple of minutes maybe to explain. There's a bit of physics here, which is that we're going to look at what happens when the system size increases. This system has 2 phases. So it's a system in which you have a first order phase transition. Okay, so there's this binodal, spinodal. We're in the range where it's the first order phase transition between inhomogeneous phase and an homogeneous phase. Okay, if you know a little bit about Canheliad, you know that the way this happens is with a nucleation. If there was no non-gradient term, you would just get a nucleation. Now, these 2 phases are slightly affected by the presence of the non-gradient term. Because, okay, let me go back. I need to finish at 12, right? Yeah, okay, so I'm almost done. We're just looking at pictures. So if you look at the solution of this equation without the noise, which is the law of large number, you see that the homogeneous phase is not affected by that term because this disappears and this disappears. But the inhomogeneous phase, the one where you have a nucleus in the system, is slightly affected because you see that this guy tends, depending on the value of lambda here, tends to push the field towards higher value for positive or lower value, depending on if you have gradients. The gradient kind of move the field. Okay? Now, if this term were not there, to find transition in this system is very simple because you don't need to do any of what you just need to analyze the property of this landscape, this standard Ginzburg-Landau analysis of phase transition, right? But it's more complicated here because you need to take into account this. When you do the standard Ginzburg-Landau, this term is not there. The way things happen is, if you look at the transition, is essentially that guy disappears. There's an anti-nucleation and it goes into you would see the bulge that disappears. But here, there is a non-trivial interplay between this additional non-gradient term and the noise. Okay? And as you can imagine, there is a way by which you can facilitate the transition by creating gradients. Because if you create gradients and the sign of lambda is the right one, these gradients, so if the noise create gradients, which is create oscillation, then it will push the system, that will help pushing the system up. Okay? So the noise need to create that, but once it's created, these guys have a tendency to kind of, right? Without the noise, everything would go back. So it's still something which is unstable, but it's better for the noise to try to do that than pushing the things uniformly. And this is like intuition, or some intuition, a posteriori intuition. When you do the calculation, this is what you see. Namely, you see that as you increase the system size, these are the same graph as before, you see that the way the transition is actually occurring is via pathways in which, as the system size increases, there is a cascade of microstructure that are appearing that help the transition. And when you look at the action, you go from this guy persists, but new branches appear. So you could continue this guy, but there are new branches that appear that makes that when the new branch appears, it makes that the action is actually not increasing monotonically with the system size, which is a non-equilibrium effect. This is not the way it happened at equilibrium. At equilibrium, it would always increase. Right? The scaling remains the same, but it does these bumps. Okay, and then I'm done. We are going to lunch. You can redo this calculation using this spin, and in fact, this was not proposed in the paper. I'm going to send you reference, but this method was first done by Eric Simonet on his own. Then we used it to do this. So these are nuclei that happen in 2D with these cascades. These are slices. This is the way this is the pathways in 2D, where you go from the inhomogeneous phase into the homogeneous phase. The equilibrium transition would just be that gas is fading out. The non-equilibrium pathways, you see that guy is actually creating structure in a ring, which is what you see here in a cut, like this is like cutting like this. And these facilitate a little bit the transition. Okay, so and then you just, because we can, you can do it in 3D. I don't know how illustrative these things, but it's the same. These are the levels set in 3D, showing you the microstructure, these nested microstructure in 3D. And it's not very clear, but they are nested structures. Okay. There are many other examples, in particular in the paper of Eric Simonet. Now we are looking at other things that you can do with that. It makes this formalism actually, for the first time, fairly easy to apply, I would say, compared to what we were doing with these classical methods. Okay, of course, this all relies on the fact that you have an action to minimize or an Hamiltonian, right? And as we know, I have discussed here a system in which taking these limit, mean field, and all that are easy, but typically the scaling that you have is not the one that allows to do that so easily. And so we typically are not in the range, or the actual physical problem might not necessarily in the range where these things would apply. Okay, though that remains to be seen. Okay, so I'll end here today. And then the next class will revisit all of this a little bit, this non-equilibrium transition, in setup where I don't want to do large deviation of the type that are here. There will be no longer small parameters, at least not small noise. And we're just going to try to see what can we do then. Okay, and we're going to look at system like undergoing motility-induced phase transition, where there's short-range interaction, no mean field limit, and see what we can do using tools from machine learning. In fact, tools borrowed from score-based diffusion model. Okay. Thank you.